I was asked this question about diffraction, and so I thought we'd go through the lecture a little bit slower just to talk about where this equation for diffraction interference comes from. So it's very similar to the two-slit interference. And so here's a diffraction of one slit. And so what you can do is you can think of light coming from two different parts of the slit. And so here we talk about 1 and 1 prime. Okay, and they have a separation of a half of the aperture. So the slit has a width of A, and so here we have A divided by 2. So these two beams of light coming from there. And if we do this very similar to how we did this with two-slit interference, we can see that there's this angle theta, and then we get this little guy here, which is the path length difference. And it's the exact same triangle as we used for two-slit interference, except now the hypotenuse is A divided by 2. So we get A divided by 2 sine theta, and so that's the path length difference. Okay, so this is the distance that 1 prime travels further than 1. And so we take that, and then of course what we can do is you can say there's a whole bunch of little paths coming that are separated by distance A divided by 2. And so our equation then says that our path length difference, A divided by 2 sine theta, when that equals to the wavelength divided by 2, half a wavelength, will have destructive interference. And of course when this happens, these two 2's cancel, and so the equation when the 2's cancel will just be A sine theta equals lambda when there's destructive interference. Then there's these rays 2 and 2 prime, and there's basically a whole bunch, depending on how you slice the aperture up, that have this same path length difference. And so the first minimum will happen at this sine theta, A sine theta equals lambda, where if you divide by the A, you get sine theta equals lambda divided by A. Now the book, and I encourage you to look at the book, so this is more, and this is page 32 and 33, I believe, and there was similar discussion about what he does. So it's a little bit different way of thinking about it. Is he actually splits everything up. So he splits the width up into 12 little dots. Okay, and then what he does is he looks at a beam leaving here, and then 2, 3, 4, 5, 6, and a beam leaving here. Okay, and so the separation here, if you count it out, this separation is just like we had before. It's A divided by 2. Okay, and so this is the first dot and the 7th dot have that separation A divided by 2. So again, that's going to lead us to the idea A divided by 2 sine theta equals wavelength divided by 2, which again, when you cancel out that 2, gets you this thing here. And then what we can see, because this would be like my 1 and 1 prime, and what we can do is we can do the second dot here. You have to forgive my arrows, they're not anywhere near perfect, but you get 2 and 2 prime. All right, and then here I can do this again at this approximately the same angle, 3 and 3 prime, and I can keep going this 4 and 4 prime, 5 and 5 prime, and then here 6 and 6 prime. So when you can see that when we split this up, all right, basically for every beam up here, there's a beam down here that's separated by that same distance, A divided by 2. Okay, and so it's going to be destructively interfering. And then each one of these top 6 beams is going to have a partner of the bottom 6 beams that's going to be destructively interfering with it. All right, and you can keep doing this, and so I talk about it here. So now I break this into 4s. Okay, so it's A divided by 4, and you do the same sort of procedure. Okay, of course, this time when you do it, A divided by 4 times sine theta. Okay, this is going to give you then, when you're done, A sine theta equals 2 lambda. Okay, and you can do this, and you can take that same picture that I just did and break this down exactly this same way. Okay, and so here we get the second minimum at 2 lambda, and so here to do that, I started here, all right, and then A divided by 4. So the separation will be 1, 2, 3 in this case here. And so right here we'll have a 1 and a 1 prime. And so these two have that same separation of A divided by 4. And if we keep doing this, so here would be 2 this would be 2 prime, this would be 3, this would be 3 prime. So these are all, if you look at them, are separated by a distance of a divided by 4, going to have that same destructive interference. And you can do the same thing down here. So this would be 4, and then 1, 2, 3, 4 prime, 5, and 5 prime, and then 6 and 6 prime. And so that's how the a divided by 4 piece works.